My name is Shawn You, and I have been with MTS for 21 years, and I have worked with Berkeley people, for many years, and with Andreas, with Steve Mahan, and it's really my honor to be here to talk about my understanding of hybrid simulation and to share, more importantly, to learn. And today, so the first presentation, I'm going to give basically an introduction of hybrid simulation and Okay. So I'm going to talk about MTS solution for hybrid simulation. And MTS has been working with UC Berkeley and other universities to develop different hybrid simulation solutions. And we have large customer bases, and more than 100 customers purchase our hybrid simulation solutions. So I'm going to talk about what kind of solutions we offer, and talk one example to show hybrid simulation, how necessary it is, and also I'm going to talk about a little bit the trend. I know Dr. Masales talked about the trend, and here, and I will offer my view and what's the hybrid simulation is going, and some conclusion. So we know that in civil structure earthquake simulation, there are different kinds for testing methods. Shaker table definitely very popular, very accurate, and in terms of simulating the ground motion. And if you have an iterative approach, you can simulate the ground motion really accurate. Then you have a big shaker table, you build your building on top of it, and it's a very accurate test, but it is very expensive. And you need a big shaker table, and no matter how big, it's not big enough. So a lot of times, although you have a big shaker table, you need to shrink down the specimen a lot. Sometimes I heard people shrink the specimen down by a scale of 1 to 50. So then nobody believes the result. So the accuracy is relative. If you have a full scale specimen, it's very accurate. If you don't have that, then it's a question. And also expensive and hard to do the test, and high maintenance, and initial investment very high. Another test very commonly done is a pseudo static test, and you just apply, you do a test on a component, and not full structure, and the loading is fairly simple, and triangle wave, and the first 3 wave, and then increase the amplitude another 3, increase the amplitude another 3 until it fails. The good thing about that is it is simple, it is cheap, it's component test, but the bad thing is the loading is not realistic. And so the simple triangular wave shape is not a real earthquake. So hybrid simulation is another test, and it divides the full structure to numerical substructure and experimental substructure. And so in the lab, you only test a part of the structure, and this part mostly is highly nonlinear, really difficult to model, and then you put it in the lab. And so the rest of the structure is in numerical substructure, and then regular FEA tools can be used. And so you can simulate all kinds of earth ground motion. And so the loading to this physical substructure is realistic. And so the test is relatively simple because it's a component test. So the loading is more accurate, and the test is more meaningful, and the analysis, analyzes the full structure. So the analysis is more accurate because the nonlinear element is tested in the lab. It's more accurate. So because of these reasons, hybrid simulation becomes really a hot topic, especially nowadays, coupled with all other effects like fire, like wind, like other factors, and hybrid simulation can cover big ground. So ITS has been involved in hybrid simulation for many years and worked with many universities like UC Berkeley, and we have learned a lot, and we have developed our hybrid simulation solutions. So, and we are so honored to be in this area and develop our own solution. And we have used hybrid simulation in civil structure, in ground vehicle. So now we are trying to push to other areas like aerospace and wind energy. So we have offered hybrid simulation to more than 100 customers. And now in civil structure area, a lot for our new systems, and we sell, and we have included hybrid simulation capability. So it's really a hot topic. So what kind of hybrid simulation solutions we offer? And in civil structure, we mainly offer three kinds of hybrid simulation solutions. One is quasi-static hybrid simulation or slow hybrid simulation solution. So in this case, so the physical substructure part only provide stiffness term, and the inertial and the damping term of a component is provided by numerical substructure. So for example, this bridge, and we test only one column. So if the specimen is rate independent, then we can test this column slowly and provide stiffness force, and the rest of the terms are provided by the numerical substructure. So in this case, because we can load this really slow because the specimen is rate independent, and so the test is relatively simple. So the actuator could be very slow, and you don't need to do fancy delay compensation, stuff like that. So the pumps could be slow, the accumulator, lines, so hardware investment could be low, and test is easier to control. So this is our basic slow hybrid simulation solution. So in this solution, and so you need to have a computer to do the calculation, FEA simulation. This computer could be, this FEA software could be in this test computer as well. So these two can be the same computer. And if you have two computers, and so then FEA model is solved here, and using OpenFresco and our computer simulation interface, and pass the command to the test computer and to the controller and move the actuators. So middleware is OpenFresco and computer simulation interface. So in this solution, a lot of our customers use OpenSeas, and because of the time constraint, I do not want to go very deep in OpenSeas. So you need a hardware. So regular controller and slow actuator is fine. You can see this actuator with a very small servo valve. That means it moves very slow. That's fine, because this is a slow hybrid test. Yeah. Some of this kind of hybrid test takes a long time because of the integration step size, stuff like that. Yeah. And the middleware is OpenFresco, developed by UC Berkeley, and I think Andreas will talk in depth about that. And OpenFresco connects the numerical model and output the command, and we developed our software called the computer simulation interface. And so this software gets the command from OpenFresco and send it to our controller, move the activity. So the feedback goes the same way. And first the controller sent to CSI, then sent to OpenFresco, then sent to analysis software. So by far, OpenSeas is the most popular FEA software used in this approach. But other softwares like Abacus, LS Steiner, Zeus NL, MATLAB, Simulink, ANSYS can all be used in this approach. So not long ago, one of our customers wants to use ANSYS to do hybrid simulation, connect with OpenFresco. So we developed the interface so that ANSYS can be coupled with OpenFresco. And in some other applications, and our customer wants to use ADAMS, another software, multi-body dynamic analysis software, to do hybrid simulation. So we developed the connection between OpenFresco and ADAMS. Yeah. Later on, I will talk about that. So this solution is very flexible, and you can have any FEA software as long as it has a user-defined element function. So you can define, if you can define element in that package, and then you can connect that package with OpenFresco, with our controller, and do hybrid simulation. So, and also we have our real-time hybrid simulation solution, and in this case, numerical physical substructure will provide all inertial force, damping force, and stiffness force. For example, this case. So a shaker table wants to do a substructure test, maybe mid-level isolation. So the shaker table models the boundary condition of the bottom layer, bottom boundary, and the actuator controls the top boundary, and then so this got to be a real-time hybrid simulation because this is an inertial reactive system. So in this case, the numerical substructure got to be, the test got to be real-time. So we provide this solution as well. So in this solution, the model got to be built in Simulink, and Simulink, and then using MATLAB coder, Simulink coder, and then convert this Simulink model to C++ code, and download to a target PC. So target PC really solves the equation and really solves the model, and then the command is stored in a StrandNet here and sent through fiber optic cable to our controller. And our controller play out the command and in real time, so the actuator got to be really fast, and then the feedback go back to the square net, go back to the target PC, and then provide to the model, and the model provide the next step command. So that's our real-time hybrid simulation solution. And for this, so we need special hardware. So we need the ScribeNet card to be put into our controller to get the command from the model in real time. And also, the actuators got to be fast, and that means you got to have a very fine-tuned actuator, and with a very large servo valve, high accumulation, big pump, and stuff like that. So hardware investment is more than the slow hybrid test. So this is a real-time hybrid simulation. So in each time click, so the analysis model has to be solved in time. Otherwise, it will not be a real-time hybrid simulation. So for that reason, the model cannot be very complicated. So one time click could be 1 millisecond. So 1 millisecond, the analysis model has to be solved. So the model cannot be that complicated. So then, for that reason, we also have a soft real-time hybrid simulation, and so this is also not MTS developed, and a lot of things are developed by UC Berkeley, and in this solution. So the analysis model can be regular non-real-time package like OpenSea, and then so OpenSea sends command through OpenFresco to a target PC. So in this target PC, there's a predictor character model running. This is developed by UC Berkeley, developed by Andreas. And then, so predictor character model running at the target PC, so it runs at a different rate as the real-time click, real-time controls step size. So that it does the interpolation, and so the model could be run at a slower, larger time step than the controller step size. And then the predictor character does the regulation and sends the command to the controller according to the controller rate. So the idea is you have another loop, control loop. So on the test side, so we have our controller with a high control rate, maybe in 1 millisecond it needs a command. And on the other side, the model cannot be run with that step size because that will require the model to be very, very simple. And so to allow some complexity in this model, so it has to run with a larger step size, like maybe 10 milliseconds. Then, so the step size for the numeric substructure and the physical substructure are not same. So this predictor character does the regulation. So it has a numerical step size from here to here. In between, you have a multiple sub-steps size for the controller. And then in each small step size, and the predictor character will check and to see whether the model is solved for here. If not, it predicts. If solves, and then it corrects to the real solution. So it predicts until the command here is solved, and then it goes to correct mode. So if it's very close to the numerical time step, and the solution is still not there, and then predictor corrector go to the delay mode. It extend the time and allow numerical substructure more time to be solved. So this is called soft real-time solution. So MTS offers all these three solutions. And to do hybrid test, and sometimes we know that it's very challenging to do hybrid simulation because it has a lot of uncertainties, and sometimes the specimen is very stiff, hard to converge. Sometimes noise reason, sometimes friction, and it is very challenging. And as I mentioned, we have 100, more than 100 customers. We need to travel all over the world to meet all kinds of challenges. So we have to make sure that, and before we go to customer side, we have confidence that we can do the hybrid test. So for that reason, so we have to simulate the hybrid test before we go to the customer side. So we have developed different methods to do virtual hybrid test, and to simulate the hybrid test before we go to customer side. So we have different methods to do that, and a lot of methods we used, and it's not that we developed. Some other people developed like this method. UC Berkeley developed this FEA adapter method, and for simulating a hybrid test, and so we just use that. And so in this example, in this virtual hybrid test example, so the full structure, full model can be divided to be two parts. So one is the main master FEA software, and another is a slave FEA software. So this part could be the real numerical substructure. This part is the testing part, except it is simulated by another FEA package. So this could be the physical substructure modeled by OpenSea or MATLAB or other or ANSYS. So in this case, and we build a model in here, OpenSea or whatever, and using OpenFresco, and send the command to another FEA package, and then the feedback comes to the master FEA model. So in this case, we can simulate the hybrid test, and we have done that quite a few times. And so this part, because the interface is OpenFresco can be coupled with all kinds of FEA packages. So this part could be OpenSea, could be ANSYS, AppGus, and this part could be some other things, could be saved. Yeah. So this is an example, and we do virtual hybrid test, and before we go to customer site to implement our hybrid simulation solutions. Yeah. So later on we will talk about more about that. And also we have other methods to simulate the hybrid test, and we have in our controller, and we can build when we do the real hybrid test, the setup is like that, like I mentioned. So OpenSea is running here, send command to OpenFresco, and send to controller, send to the real test system. So this is the hybrid test we plan to do. And then, so this virtual station can be modeled using calculation channel function. So inside our controller software. So the we build a virtual station inside this controller, and then the OpenSys model sends command through OpenFresco to this virtual station. This virtual station is built by calculation channel. Later on, I will talk in detail. And then, so this calculation channel is a very complicated, it has a complicated functions, can build a pretty fancy virtual station, and then through this kind of a virtual station, and then we can simulate the hybrid test before we go to customer site. So this calculation channel interface is here, and you can write a pretty fancy programming here, simulating all kinds of effects and like friction, noise, and delay, all kinds of things. And to do real-time hybrid simulation, and usually, so there's a delay, there's a roll-off. So for the low frequency, if you give a command, and at the low frequency and command feedback, matches are fairly good, and you cannot see the differences. But for the high frequency, and if you zoom in, and you can see the command and feedback, it has a phase lag, and the amplitude is off. So to do real-time hybrid simulation, you have to compensate for this effect. Yeah. So, and there are different kinds of compensators, and we have our own. We have the different delay compensators and self-adaptive adaptive compensator. So and feed forward and frequency based, and all kinds of compensators can be used. And so this is a compensator and developed by Dr. Tay of Old Dominion University, and this is a self-adaptive, has 3 parameters. During the real-time hybrid simulation, those 3 parameters can be self-adaptive, self-learned, and you don't need to do pre-tuning or anything like that. Very simple, very good. So we are very happy to use this compensator. And next, I'm going to show an example of a hybrid test. So this work was done by our friend at Swinburne University, and this hybrid test, it has a numerical substructure for this free structure, and the physical substructure is just this column tested in the lab with this 6 degree of freedom loading system built by MTS. So the interface point is here, and during the hybrid test, hybrid simulation, numerical part and tells the physical part, the boundary condition here, the displacement, and in the lab, through this loading system, it realized this displacement at this point, and then measure the force and feed the force back to the numerical substructure, and then calculate the next step. So very, very good hybrid test. And they also did a regular quasi-static test according to some predefined, specification. And so this is a quasi-static test, and this is hybrid test. And a hybrid test is simulating one specific earthquake. And quasi-static test is just rectangular loading, and you can see the damage. So the quasi-static test has a lot more damage than the hybrid test. And this is a long story, and the the result is, and if you use a hybrid test, the result, the damage is a lot less, and if you use a process static test, and the damage is much higher. So the drift, ratio for the process static test is twice as much as the hybrid test. So from here you can see that the hybrid test simulating the real earthquake is more realistic loading, and the process static test, and it's a man-made loading, and cause as a result, so the damage is a lot more. And also at the Swinburne University, they use hybrid tests to evaluate all kinds of reinforcement method, and to make this column more stronger. So this is a example of a hybrid test, and shows that the advantage of a hybrid test over process static test. And I'm sure during these 2 days we will talk a lot. We will see a lot more examples. And next, I'm going to talk about the trend of hybrid simulation. So one trend I see is coupling the hybrid test with the shaker table test. And I see more and more shaker table to test a substructure. Like Dr. Masales showed, and their test, they use a shaker table to test one part of the electric component. Yeah. So we see more and more of these kind of applications, because the building is very tall, and if you test the whole building, and you have to shrink down the specimen a lot. And if you can test a part of the building with the shaker table, rest of the structure, and model the analysis software, and then you save a lot of money and energy, time. So this is a hybrid test that we did at Tongji University, and so in this case, and so the specimen is a part of the bridge structure, and the foundation, and the foundation is modeled by FEA, and so the bridge column, bridge deck is tested in the lab. The weight on top of the bridge deck is in the analysis model. So here, so the bridge column deck, you see there's no weight. The weight is in the analysis substructure, and the inertial effect is applied by an actuator. So this is a shaker table coupled with the loading actuator hybrid test. So we see one more this kind of application. So, and I think Andreas will talk more about this application. So I will really, I will not talk in good detail about this. So we see another trend. So hybrid test to control multiple degrees of freedom. So hybrid test coupled with the degree of freedom control. So what is the degree of freedom control? And so to show that, I have a picture here. So there are two actuators. So if this actuator moves and this doesn't, so this point goes through an arc. So it's not pure vertical, and it has some horizontal movement as well. Same thing. So if this actuator stay here and this actuator move, and then this point goes through the same arc. So one actuator move two degree of freedom motion. So degree of freedom control is to control, in global degree of freedom. So I control x, and then both two actuators move together to make sure that this point moves horizontally in x direction, no y movement. Same thing, y and rotation and So DOF control is control any point in global degree of freedom and in 6 degree of freedom. So, for example, this master system and with 8 loading actuators, and so we have a control algorithm to make sure that any point can be controlled in global degree of freedom in any degree of freedom. So this is called the degree of freedom control. So MTS has a special software to realize that. So no matter how many actuators you have, and overdetermine, no problem. And you have some in load control, some in displacement control, no problem. And you have some in acceleration control, that's no problem also. So we have this degree of freedom control software, and we see the trend. The customer wants this degree of freedom control software to be used in hybrid simulation more and more. So, for example, this case, and this is a system we just delivered to Sichuan Highway Research Institute in China. So they have 6 actuators down here and a table here. So then this this specimen is on top of this platform, and then we can use this degree of freedom control software to control any point in global coordinate system. Some in load, some in displacement. So this is a degree of freedom control example. And so this is a Polytechnic University 6 degree of freedom control loading system. And later on, Martin will give a presentation about hybrid test using this system. And so this is a 4D DOF control system. So previously, all these systems are 6 degree of freedom. And so this is a 4 DOF system, UC Berkeley, did, and with 4 loading actuators and controlling 2 displacement and 2 rotation angles. And these kind of applications can be easily done by our degree of freedom control software. So, and a lot of other different test configurations, and use our degree of freedom control software can be easily achieved, like this system, 2 actuator here, 2 actuator angle. And with the large deformation, could be very complicated to control 4 degree of freedom, but with our degree of freedom software, this is no problem, very easy. So another trend we see is hybrid simulation is used in other industries like auto industry, and so we have a car here, and the damper is really nonlinear component is active, and it is coupled with the computer inside the computer. So it's really tough to test those dampers, and then So we have a car modeled in numerical substructure. The damper is tested in the lab, and then this is a real-time hybrid simulation. So this product is called the four-corner damper system. And also in wind energy, and people use more and more hybrid simulation because composite components, and over the time it will degrade, and it's really some components are nonlinear and hard to model, and then we test a part of the structure and model part of the structure. Some specimens really huge, and some of the blades are 120 meters long. So the lab is not long enough, and then so they only test a part of the blades and model the rest. Okay. So, and also we see in aerospace, and more and more hybrid tests are done, and so this is a hybrid test for the helicopter damper, and done by University of Bristol, and at MTS we are actively developing hybrid simulation solution tailored for aerospace industry. So, in conclusion, hybrid simulation makes the computer simulation more accurate because the really nonlinear component is tested in the lab, and it makes the lab testing more accurate because the loading is calculated by FEA model, so it's a real loading, realistic loading, and MTS has the honor to work with a lot of universities, mostly UC Berkeley, and we developed our hybrid simulation solutions. We helped our customers, and we provide different solutions to our customers, and in civil structure, in ground vehicle, in wind energy, and hopefully in aerospace. So that's my presentation. Thank you.